Our next speaker is Dr. Alon Kaufman, co-founder and CEO of Duality Technologies. Duality expertise is machine learning in encrypted data, and Alon will tell us about the challenges and opportunities.
Excellent, thank you. I'm going to walk around. That's how I do these things. So I'm going to try and talk with this microphone and move it with the hand. Thank you, everyone. Hope you had a good lunch. Hi, my co-founder's husband. So thanks for joining us. I used to be at RSA. I was part of the Cyber Week, and I have to say that seeing this way AI Week has started with such a lot of energy is really a great pleasure, and I'm happy to be talking here on an area that someone combines these two fields. And we're going to talk today about machine learning and encrypted data, and I'll present myself a little bit later, but conceptually machine learning and encrypted data are somewhat very, very different fields that have also a lot in common. So if you really think about it, machine learning is all about finding patterns in data that looks noisy, random, or whatever. And people, like the quote, finding the needle in the haystack. So machine learning is all about finding this needle within the noise. And encryption is exactly the opposite. It's about taking a message, taking a signal, and hiding it in noise. So taking the needle and hiding it in the haystack. So in some sense, it's like water and oil, two very different things. But on the other hand, they're very similar because they actually do the opposite. And it's not surprising that people like Shannon and Turing and so on were great encryption people and great machine learning or information theory people. And that's basically what we're going to talk about today. But there is a challenge. People that learn machine learning, and I call myself as one of them, typically don't touch encryption and vice versa. And encryption is even something that for people that don't do it sounds very remote and distinct and like geeky somewhat. So as an AI crowd, how many of you feel comfortable with encryption? Well, we're getting better. How many even know what encryption is? Okay, great. So the whole talk today is going to be about merging these two worlds. It's more introductory kind of a discussion. And I want to basically describe the potential around it, try and convince you that it's critical for the age we're living in, and also bring you up to speed on what's happening there. But I do have to say, although we don't know very much about encryption, most of us, we use it in our day-to-day, of course, all over. And encryption was actually the driver for this whole e-commerce world. So the ability for me to buy something from a remote person and send him a credit card, that's what was holding e-commerce back. And an algorithm called RSA, which is an encryption algorithm, is actually what enabled that and made that whole field bloom. And so that's exactly what we're trying to do here is find the challenges that require encryption in this world of AI and enable collaboration in AI, and I'll explain in a second what we mean. But first, a little bit about myself. So as I said, I actually come from the machine learning world. My PhD is in the Hebrew University in computational neuroscience. I've been doing what used to be called data mining, then machine learning, then data science, now AI, done all these things in different places. My last role before founding Duality was actually with RSA, and that's where I started to get into security. So initially, I was leading data science for RSA, and leading data science for RSA meant building models to do fraud detection in the financial space, building models to do identity theft detection, cyber attack detection, and so on. And at some stage, I got responsibility also of RSA's research, which had a bunch of encryption people. So RSA is an encryption company. And so I found myself with a data science team and encryption team. And at that time, RSA had a big challenge. So all our models, let's say the fraud detection model, we wanted to build our models in a hosted environment, like I'm sure all of you want to. So we wanted all the data to come to us at RSA, build our models on it, build online learning nice models, and serve our customers. However, if it was financial fraud, if it was identity theft, data leak, whatever it was always on sensitive information. So for example, the banks never wanted to send us their transactions because it's sensitive information. And if they did send, we had to be PCI compliant, so deal with sensitive data. And RSA never wanted to install our models on-prem, for obvious reasons. So the question is, how do you bridge these things? How do you actually enable to offer predictive analytics, AI, machine learning, name it whatever you want, without the need to really see the data? And that's where we combine these two worlds at Duality. I'm co-founded Duality with 5 co-founders, leading worldwide professors, Professor Shafi Goldwasser, which some of you know with the Turing Award, and Vinod Vaikunatana, an MIT professor, and Kurt Roholf out of the States. And in Israel, it's myself and Rina Shainsky, our chairwoman. And we co-founded Duality to solve exactly this challenge. But before we go into Duality, I want to continue and give a little bit more background. So this is the classical machine learning process, and hopefully you all know it, and if not, you're in the wrong room. And let's take an example, like this is a nice example of a dermatologist level classification. And the process, as I'm sure you're familiar, you take a lot of lesion images, you get expert to define which of them are benign, which of them are malignant. You may get several experts to build this very quality kind of data set. And you can go and build a model that at the end of the day, you can just take a picture of your lesion with your mobile, send it somewhere, and get probably the best classification of cancer, skin cancer. Now, this is, of course, amazing. I mean, now we're sitting in a house, we don't have to go to a doctor, and we get better level classification of skin cancer. So this application, you have to admit, is amazing. And moreover, you can now upload your pictures to Google and get a full body scan and so on and so forth. So we're not there yet, but that's where the world is going. So great examples. Another example, for example, in the DNA space. For example, as I'm sure you know, today companies are starting to take DNA samples and do all kinds of personalized things. Personalized diets, personalized risk factors, personalized dating or matching services, and so on and so forth. And how it's done exactly the same way. You take DNA data, you label it, rank it, you build a model, and you get the service. And although today these things are still starting, I hope in 10, 20, 30 years from now, based on our DNA, we'll get personalized medicine. We'll be, our children will know exactly what to go and learn, what kind of food to eat, and so on. So these are amazing stuff going on, as well as, for example, taking DNAs and building machine learning algorithms to actually reconstruct faces. So imagine how this can change finding criminals. And many, many more. And hopefully many of you in the room are building these nice models which definitely change our life for good ways and provides a lot of value. And this actually shows the beginning of what we now know, a huge change of the powers in the market towards data. So this, I'm sure some of you have seen other types of images. These are the top 5 companies in the world, 5 years ago and now. And as you can see, 5 years ago, Apple was there, but there was the oil companies and financial companies. Today, all 5 companies are all data companies or information companies. And by the way, if you look 10 years back, it's even no data companies and so on and so forth. So there's a huge shift of power in the economic world, in the commercial world, towards data powering the economics and today. And I'm sure you've heard the quote, data is a new fuel, and so on. And at the same time, when you have power, you also have competing groups. So just imagine, we take that lesion example, which is great for us. We can find cancerous lesions. But just imagine if Google, and sorry I'm picking on Google for no reason, they can basically scan all pictures they have of all of us and know, before we know if we have cancer or not, what type of cancer, how old we are, where we live, how much money we have. Just for that simple example, see how powerful it is. And we've really just starting to see the beginning. So the companies that own the data, the companies that own the information, are the companies with all the power, and that's also where it starts to become risky. And it's a very complex challenge, because I don't know if anyone you heard about this project that uses face recognition to help children that lost their parents to reconstruct and find their parents. So this is a great thing. But on the other hand, I'm not sure we want our children's images running all around. This is an example where Facebook can basically predict if two people are in a chat, if they're going to become a couple or not, before they know. Okay, so you know, this is the single, this is in a relationship. Facebook knows before we know if we're going to get in a relationship with someone or not. And obviously that means that they can manipulate it. And we've seen them manipulate things. And this is before, you know, eyeglasses, all the wearables, and so on and so forth. So we live, I think you get the message. We live in a world where all this data can do tremendously good things for us, but at the same time, very, very risky in terms of the power we give, and many, many more examples. I have to say, this is like a recent one. I hope you've all seen. Google already is collecting huge amounts of healthcare data, and the challenge is that, you know, Google is probably protecting our data, but people that we don't know are using our data in different areas for different projects and so on. And the reason I'm so much focusing on healthcare data is because, first of all, we haven't even started to see the big value of AI on healthcare data. We're just starting now to see these things, and that's before you start to combine genomic data and clinical data and wearable data. I mean, the world is going to change dramatically, but also healthcare data, very different than other types of data, like financial data, that once you lose your data, basically typically decreases. In healthcare, it's actually the opposite. So let's say I lose my credit card and someone can use it. From the second I lost it, its value decreases. Because the minute, you know, I figure out it's lost, I can cancel it. I didn't figure it out, someone does a transaction, I can then see it and then go and cancel it, and so on. So as time goes by, the fact that I lost my credit card is less important. But without genomic data, for example, it just gets worse over time. Because first of all, I can't change it. So my genomic data is out there, my DNA is out there, I can't change my DNA anymore. And the value that is going to be given on our DNA, we don't even know yet. You know, who knows what 50 years from now people are going to do with DNA. And moreover, if my DNA data is out, so half of my kids' DNA data is out. And I don't know what's going to happen in 200 years' time with that kind of data. So it's a very different mindset. The world is all nervous today about Facebook and everyone seeing our chat data, our financial data, and so on. But healthcare data, and specifically genomic data, is a whole different story. So I didn't come to ruin the party of AI. I think the country is putting in investments, you are putting in investments, and I think it's very important to invest in it. I think it's a good competitive edge of Israel. And we also have to understand that AI or machine learning is all about collaborating, because the entities that hold the data typically don't have the models. You know about the shortage of data scientists and so on, and many of you probably represent companies that provide AI and typically don't have the data. So you want the data owners to collaborate with the model owners and typically run on infrastructure of a third party maybe. And so you have to collaborate by definition here. And if data is so powerful, and if models are so powerful that they can change elections or predict, you know, relationships and so on, we live in a world where all these sides have dramatic power, and we have to trust the way they work together. Now, typically when people talk about trust and security challenges and so on, they go to the malicious side and the cyber side. Let's leave that for a different talk. I'm just talking about the simple fact that if our data is so precious to us and to others, we need to at least know what's being done with it, and at least control the usage, and at least make sure that our privacy doesn't leak. So I'm not talking about someone hacking data, poisoning data, adversarial AI, which is a totally new topic. I'm talking simply about companies that own this huge precious thing, controlling what's being done with it. And in this context where you have to collaborate on it, means that you have to share it, this becomes critical. And that's where we start to look for solutions, because today that trust has been broken, as you read day and day in the papers. There's been a lot of legal work, compliance, regulation, like GDPR, for those that you know in Europe and different things in the States, which don't allow to simply share data or don't allow to share it for all use cases. So it's becoming a much more harder complex. And if you heard Ben Lorica, GDPR already decreased investments in Europe. And so we can't stop AI. We don't want to stop AI, but we can't let it just continue as is. And the question is, okay, so how can you collaborate actually in a secure way? So let's just think conceptually about collaboration. If I want to collaborate with someone, I can just give him my data. Of course, that's a trust model. But today, with the new regulations, you can't really do it. And as we all know, after scandals that we've seen around misuse, you probably don't want to do it, even if you could. Another way is you can always find a trusted third party. So you can always, let's say I want to share a model with Noam there. I have data, Noam as a model. We can always go to a third party we trust, sign a lot of legal agreements. I'll give that third party my data. Noam will give that third party his model. The third party will do the work for us. That's possible. The challenge is that, again, we have to trust. I don't know how many of you can trust even the big players. And of course, it's much, much more expensive. The third way is basically to anonymize data. So that's what's being done today. You take the data, you strip out the names, and it's all good to go. But we all know you can't really anonymize personal data. I just showed you. You can take genomic data, you can delete my name, but the next thing you can reconstruct an image of myself. You can take my geolocation data, you can delete my name, but you know exactly where I live, exactly where I work, exactly where who my friends are. So de-identifying the data, although regulation still talks about it, it's clear to everyone it's not good enough. And then there's like the ultimate solution for security, and it's what's called encryption. So encryption, in simple sense, it's taking data, locking it in a box. And once data is in a box, no one can touch it. It's great. But the big challenge there is when the data is in the box, you can't really use it. Up until a few years ago. And that's the whole thing I want to talk about. Today, we acknowledge that there's a huge driver with good reasons, with financial forces to collaborate on data, use third-party applications, use third-party infrastructure. Sometimes even the government enforces us and makes us do audits and so on to collaborate. So on the green are all the good reasons to collaborate. There's huge security challenges and privacy challenges to collaborate. And now the question is how you settle it. And this is where I get to a whole new field that has been emerging and taking up, for a very long time, and now it reached a peak. It's called secure computing in general, and homomorphic encryption is like the holy grail in this space. Homomorphic encryption essentially allows you to analyze this encrypted data. So to take encrypted data, and while it's encrypted, analyze it and get some results, and I'll show you some example. It's not taking encrypted data and creating patterns out of it. It's not doing machine learning on encrypted data. It's actually analyzing the encrypted data in an accurate way. Now, this has been something that's been worked on in the academic world for many, many years. In 2009 came out like the proof that this can be done. It was still very theoretical, but it showed that yes, you can encrypt data, meaning transfer it to a new space in which it's encrypted and apply to their mathematical operations. Of course, it was very theoretical and not really practical, but from 2012 going up, there's been major improvements, and more companies have been getting into the space, or big companies or startup companies, until just recently, Gartner has already announced the category, starts to talk about cool vendors, companies are buying these solutions and so on. So we finally, 10 years after the original invention, got to the stage that this is now commercially viable to run models on encrypted data. Now, it may sound to you even counterintuitive, but this type of encryption is even stronger than other types of encryption we're familiar with. This is not only an encryption that you can analyze on with it, it's also stronger and what's called quantum safe, but I'll leave that for questions afterwards. So what is it? It basically allows you, let's say I have an MRI image and someone has a machine learning classifier. I could basically buy or consume this classification without the side with the classifier learning anything about my data. That's like the simplest thing. I have data, I want to consume some value from you. I can consume it without leaking any bit of information on my data. That's essentially what it does. I'm skipping forward. This is like a cartoon of how it's done. But I want to give you like a more kind of intuitive examples that always people ask me, hey, what is homomorphic encryption, how it's done, and so on. And this is complex math, so obviously it's not so easy to explain, but the way I like to explain it is the following. Let's say I have a jigsaw puzzle of 1,000 pieces. And you are an expert in doing jigsaw puzzles, I don't. I want you to do the puzzle for me, but I don't want you to see any of my pieces of the puzzle, and I don't want you to know the picture there. You can know that there's 1,000 pieces, you can know that there's a puzzle, but you're not allowed to see any specific piece or the picture. So homomorphic encryption enables me to take my puzzle, put it in a box, lock the box, put the key in my pocket, ship the box to you, and homomorphic encryption like magically enables you to like push your hands into this box, build out this puzzle without seeing any specific piece, and once the puzzle is ready and it's still in the box locks, you send it back to me, I open the box and find the puzzle there. So you've done the puzzle for me, but you've never seen what came out. And that's what homomorphic encryption is about. So it's not that someone does an analysis and can see the result and can backtrack and whatever. It's purely the entity applying the computation never sees the result. Now, I know some of you are sitting in the chair and it can't be and how come and so on. So two things. One, I'm going to give you a little example that gives you the intuition. And two, afterwards we can show you a demo and see this really working. But I like to give this intuition because especially machine learning people think that we analyze the data or it's a probabilistic model on the data. And no, this is accurate computations on data while it's encrypted. So let's take a little example. So first, conceptually, what actually happens? So encryption is taking, this is the plain text world, the world we live in. This is the ciphertext world. And encryption basically moves numbers or things from the plain text world to the ciphertext world. So the key takes these numbers, locks them in a box. And then if you want to go back, you decrypt with a key. And homomorphic encryption has a property that if you apply computations in the ciphertext world, they're basically equivalent to things in the plain text world. So if we play this out, if you go and add the encryption of A, which you don't know what it is, to the encryption of B, which you don't know what it is, and multiply this by the encryption of C, you don't know what it is, you get a result which you don't know what it is, but when you decrypt this result, you go back and you get the result of A plus B times C. So this is the mathematical, simplistic formulation of this problem. Now, let me give you a little example, a really, really simple example, but it will give some intuition. Let's say I have two numbers, 5 and 7, and I want you to add them for me. I don't know to add, only you know to add. I have two numbers I want you to add. I don't want you to understand that my numbers are 5 or 7. I definitely don't want you to know the answer is 13. Not sharp enough today. So I'm going to take a secret key, a large secret key. In this case, it's going to be a small one, but it's typically a 10-dimensional kind of number. And the way we're going to go encrypt 7 is we're going to choose a random multiplier of this key. So the key is 94. We're going to choose a random multiplier. Let's say it will be 3. So the encryption of 7 is going to be 3 times 94 plus 7, which is 289. By the way, the next time I'm going to encrypt 7, it's going to be a different number. So every time we encrypt, this is a probabilistic encryption, the answer will be different. Because we'll choose a different random multiplier, of course. Now, I'll go and encrypt 5 as well. Let's say the random key this time is -2, and what we get is -183. Now, these are the two numbers, the encrypted version of my numbers. I now send it to a third party to do the adding for me, but that third party doesn't know my key. That third party only gets these two numbers, 289 minus 183. He doesn't know what they mean. He can go and add them. He gets 106, but he doesn't know what 106 means either. If you give me back 106, of course, I know my key, which is 94. I do the modulo and understand the answer is 12 and not 13. So this is a little small example. Obviously, homomorphic encryption that took decades to develop and is a very, very complex math is a little bit beyond this, but this is the idea behind it. It's accurate computations on data that's encrypted in a strong manner without the entity doing the computations ever seeing the answers. And yeah, we're going to run forward and leave time for questions. And this is the basis on which Duality, the company I lead today, was founded. And the types of things that we do at Duality is, for example, let's say, going back to the fraud example, I am a bank, I have financial transactions, you have a risk model I want to consume. You're not prepared to run your risk model on my premises. I'm not prepared to give you my data. And with Duality, what happens, we take the data on the bank's premises, we encrypt it, send it encrypted to the model owner or the environment where the model runs. The model, using our technology, the exact model you wrote in Python, is now run on this encrypted data in an accurate manner. The result is never seen, sent back, decrypted, and used. And there's several variants here which I won't go into. I can encrypt my data and send it to the model owner. We can do the opposite. I can encrypt my model and deploy it on-prem or in the edge. So if I have a model and my model is my IP, my model is what I've spent the last 15 years developing, but I have to run this on the mobile or some environment which is a non-trusted environment, I can encrypt my model. And of course, there's much more interesting examples of linking data and so on and so forth, which I don't want to go in now. So in summary, and to leave you a few minutes for questions, we live in a world today where AI is here to stay. There's a huge wealth and good values coming out of AI. There's a huge challenge that is starting to rise, and we've seen it in the last 2 years, and it's really bothering regulators. It's really bothering data owners. It's bothering law enforcement, ethics, and so on. And there's basically, we have to come up with a technology way to solve this challenge of collaborating parties that can't trust each other, but in order to live with the advancement, have to collaborate. And that's exactly where this whole space of secure collaboration comes in. And by the way, there's several technologies in the space. But that's exactly where these technologies come in. I'll just take a quick picture. Those who are interested, here are a bunch of software libraries in the space of secure computing. Specifically, we work on a Palisade, which is an open source library that we have developed. But those of you that are coders, this is a good screen to take. And with this, I want to thank you and take questions if you have.
Any questions?
There was one up there.
Is it feasible to make this computation on encrypted data? Because it should take longer to make the same computations on encrypted data.
So yeah, so great question. So first of all, it's feasible. We have customers using it. I can show you a demo afterwards. And no free lunch. It's more expensive. So a few years ago, it was like 5 orders of magnitudes more expensive. So now it's down to 1 or 2. So it's still more expensive. But this is feasible. We don't do anything real time yet. We do batches. We do numeric and not video and so on. So there are limitations still. But this is feasible and used today in banks, insurance companies, and healthcare companies. Shout. So you can also do training with us. It depends what type of training. If you do, deep learning training that in the clear view, it takes you a month to do, so this won't be used. But simple training, decision trees, logistic regressions, things like that, we can do training as well. Also, the more complex, it just becomes infeasible in terms of practicality. There's no inherent change in the algorithm, at least. Yeah. No, just performance, which is a challenge. Yes. Sorry, yeah. You get the right to choose. Great. So, like in my puzzle example, the data is encrypted, but has to be full agreement between the parties. A, that we're collaborating. So this is not a backdoor. I can't encrypt your data and send it. So the agreed parties know that they're collaborating, and the data schema is known. That's critical. We have to know the data schema. The data inside is encrypted, but the data schema is known between all sides, and that's very, very strict. I mean, otherwise we could really, you know. So we focused on inference, but also customers do use things like simple SQL queries and simple models and simple statistics. So it basically depends what they do. Since we sell to financials, healthcare, and so on, it's a lot of decision trees, XG boosting things, statistics, and so on. So it depends, but we have like a CNN example running on data as well. Inference.
Last question.
Yeah, we have example on images. We don't have commercial deployments on images. We have a system running on images. It's much more complex and expensive, but we have like a Cypher 10 example on images. No, we just like done a benchmark there. We have no customers today with images looking at this. I think images is a little still more complex, but yeah, going forward, I'm sure there'll be, because all face recognition, we have an entity which people can imagine wanted to use the cloud face recognition, but without disclosing one of the images they upload into the cloud to do a face recognition. So yeah, there are examples. It's still a little tricky for the technology.
Okay, thank you, Alon, very much.
Thank you. I'll be happy to take extra questions.
The next session will start at 2:30.